This is the 9-7 podcast where we're going to talk about the law of conservation of energy, which is not that much different than the law of conservation of momentum. And once again, it states that you can't destroy or create energy, but that energy can be transferred from one form into another, and the total amount of energy that's in a system never changes. If you remember with momentum, we said it couldn't be created or destroyed, but momentum could be transferred, and the total amount of momentum never changes, so it's very similar. So we're more concerned not knowing, in this section, about knowing what energy is, as much as we want to know how it transforms, how it goes from one object to another. So let's look at this bow and arrow example. What's going to happen is she's going to pull back on the bow, which is going to she's going to do work on the bow, right? She's going to stretch the bow, which is going to do work on the bow, and then the bow then is going to have potential energy. That's going to be elastic potential energy, and then when she releases the bow is going to do work on the arrow, and it's going to give kinetic energy to the arrow, and this is going to be equal to the potential energy that the bow had. And then when the arrow is released, the arrow is going to give its kinetic energy to wherever its target is. So we can match with the conservation of energy. We can match the small distance the arrow moves multiplied by the average force of impact. It's not going to quite match the kinetic energy. But we do know that the arrow and the target are a bit warmer by the energy difference, and so the energy that changes from one form to another will be without a net loss or a net gain. We can't destroy or create energy. So this is what we call what we're studying here is the law of conservation of energy, and the quantity of the important point with any of these systems is that the quantity of the energy does not change. Now, for any system, the one item that's not going to change is energy. You can change form. It could become kinetic to potential, and it could go from electrical to thermal, but in the end the total energy of that system has to remain the same. So let's look at this example here. We have a little skate, and we wind it up, and we end up putting 10 joules of stored potential energy in this spring here. And as the spring unwinds, 8 joules of that kinetic energy 8 joules of that potential energy are going to be transferred into kinetic energy, which is going to make the little cart go. But that still doesn't account for 2 joules, and those 2 joules might go into the form of heat. The friction right here, where the key turns, friction here with the springs. There's a couple gears, there could be friction there. You get a friction on the wheels, on the where the hubs meet. You get a friction between the wheel and the ground. It's all where the energy is going to be lost due to friction. Let's look at this pendulum. When we have a pendulum, we hold it up to one side. It has a height. It has a potential energy, and it has the potential of swinging down. And as it swings downward from this starting height of this dotted line, it loses potential energy. You can see its potential has gotten smaller, but it's going faster, so it's gaining kinetic energy. When it reaches the bottom of the swing, where it's at the furthest point down, it can't go any further, it has a lot of kinetic energy. This is the spot where it's going to be moving the quickest. And lastly, it's going to swing back up, and it's going to come to a stop at the other side of the pendulum. And there it has a height again, so it's going to have more potential energy again, and you can notice it has no kinetic energy because it's going to stop. Let's look at this woman as she jumps out of a building. When she's up at this height, she might have a potential energy of about 10,000 joules, and she's not moving, so she has no kinetic energy. As she falls, she loses potential energy, but she gains kinetic energy, and in the end, this is 7,500 joules of potential energy, 2,500 joules of kinetic energy. It still has to equal the original 10,000 joules. And as she falls, here she's halfway down, so her potential energy is going to be half because her height is half, and now she has 5,000 joules of potential energy. Therefore, she's going to have 5,000 joules of kinetic energy. Once again, the total energy is 10,000 joules. Now, skipping to the end, when she reaches the ground, she has no more height, so she's going to have no potential energy. However, she's going to be moving at her fastest speed, which is going to be kinetic energy then is going to be 10,000 joules, which is the same amount of energy she started with. Here we're talking about atoms being energy, and the way a nuclear reactor works is that when an atom is rearranged itself, say for instance it split or it fuses, then energy can be released. And one of the places where we have that type of energy release is in the sun. The sun is releasing some of its nuclear energy within its atoms into radiant energy, which we see as light. Now, in a nuclear reactor, what we're doing when we're splitting or fusing the atoms, as we talked about, is the energy then is transformed into heat, which then we use to heat water, which we then use to run a turbine, which we then create electrical energy, etc. Looking back at the sun, we can see that the sun causes hydrogen nuclei to fuse together to become helium nuclei, and when you have this infusion, it ends up producing radiant energy, some of which reaches the earth, and then when it falls on the plants, this is light energy, falls on the plants, the plants then convert that into energy that they store in the plant itself, and then when the plant dies and gets compressed, it then can become coal or oil or natural gas, which then we can use later on for another form of energy. It becomes a part of chemical energy. So you can see from that we get our energy from the sunlight. There's another part of energy in the talking about energy, is that the sun's energy is used to evaporate water. The water then goes up in the air where it gains potential energy, and then it could become back down to earth, kinetic energy. It might get trapped behind a dam. Once again, now we have potential energy. So you can see how the energy changes throughout. Energy now has, the water behind the dam has potential energy, and then it could be used to run down a river, go through the turbine in a generating plant, and then we end up with electrical energy as a result of that. We can then take that electrical energy coming into your home, use it to light, which now we're using light energy. We could heat the home. We could cook things. We could operate electric toothbrushes, whatever. We're transforming the energy from one form to another. So the law of conservation of energy states that you cannot create or destroy energy, that you can change its state from one type or another. You can transfer the energy, but in the end, the total amount of energy has to stay the same. It all has to be accounted for, and we can remember that the energy can then be lost in terms of heat, friction. We've seen that too.